This is joint work with my colleagues from a bunch of different fields and a bunch of different areas. Here's what we use blue waters for. We want to analyze the risk of infection spread due to movement of passengers during air travel, because a lot of diseases are spread due to proximity of people having the disease. So that is our basic goal, and this is our project. There is more information available on our project page. Basically, the most important thing, our innovations arise in modeling the movement of passengers and in some of the performance optimizations that are more generalizable rather than focus on this particular application. We also use conventional techniques. Once we have the passenger movement done, we use conventional techniques to model the spread of infection. So our motivation is air travel is an important factor in the spread of many diseases. And that had been called, for example, in the recent Ebola outbreak, there were calls for banning flights from Ebola infected areas and so on. These can have a huge human and economic impact. So what we want to do is we want to try to reduce the likelihood of infection spread without without disrupting air travel. So you maintain the same air travel volume, but you reduce the amount of likelihood of people coming in contact with each other, so that there's less likelihood of the disease spreading. Basically, we want to analyze the impact of different policies. For example, can you change the boarding procedure? Can you change a disembarking procedure on planes and reduce the likelihood of infection spread? Right? So there are many different criteria we use. And it matters because we can actually provide insight to decision makers. And if there's a disease outbreak, we may be able to take steps to reduce the likelihood of infection spread without disrupting air travel. The problem with current models is they're basically focused on scientific understanding rather than on policy analysis. One of the important aspects in if you're dealing with the real world situation and you want to take action is that there's a lot of uncertainty. One is the data may not be available, the data may not be inaccurate, and a lot of the impact of decisions depends on how people react, and people are inherently stochastic. You can't really predict what people are going to do. Okay. So the other is they use aggregate data, and if you use aggregate data, there are only a couple of things you can do to reduce the infection spread. You can reduce the aggregate traffic, right, which disrupt our travel, or you can use screening at airports and so on to reduce the number of infected people who are traveling, right? So we may be able to actually do better than that. I'll show you soon. Okay, so the net result is typically models have often had very inaccurate predictions. Public health agencies I talk to often are very skeptical of predictive models. Okay, so what we instead try to do is we try to identify vulnerabilities. So what we say is one is, instead of using aggregate data, we use a fine scale model of human movement. The other is we parameterize sources of uncertainty. So instead of saying this is going to happen, what we are saying is we'll do a parameter sweep so that generates all feasible scenarios that could happen. So if a policy is robust, then it will lead to small amount of disease under a variety of situations that can happen. We don't know what is going to happen, but if under most of the circumstances it leads to less disease than the current policy, then that policy is more robust. Okay, so we are trying to avoid a vulnerability in the system. A key challenge over here is the parameter space is very large, which leads to high computational cost, especially when the number of parameters increases, you have a high dimensionality, and so the space becomes very large. Okay, so we use blue waters for the computational power, so that ideally, if there's a national emergency, we want to be able to provide solutions very fast. Because usually what happens is that a model that we have developed may not actually be very accurate in a new situation. We have to iteratively refine it and so on. So having good computational power is important. Okay. This is the basic idea we have. We use certain procedures. Based on that, we have a model for human movement called the SPED model that tells us how people are moving. And based on that, we can find out how many people became close to some other people and so on. Once we have the proximity information based on the trajectories, we can input into a conventional disease spread model to get the number of infected persons. Then from based on what happens at a given airport, we want to get some global data. Ideally, we would like to feed it to a phylogeography model which uses genetic and geographic information. Right now, this is an independent component. We haven't linked that. Instead, what we do is we just aggregate the result for each airport and get the result for the whole global scale. Okay. And of course, we would refine the model based on this. Now, we can answer questions like, can changing the plane type reduce the likelihood of infection spread? Can changing boarding and disembarking procedures change the disease spread? Can changing airport layout and procedures change the disease risk and so on? Okay, so these are some of the questions we have answered, at least to some extent. I will show you the results at the end of the talk. And it has had, we have been in outreach with airports, public health agencies, the International Civil Aviation Authority and organizations and so on. We have also got a lot of news coverage in the regular press in terms of broader impact. In particular, The Economist had a pretty decent article on what we did. Okay. So I'll talk about the passenger movement model. It's basically based on social dynamics, which is like molecular dynamics. Humans have a tendency to go towards their goal, right? And they also are hindered from reaching their goal due to other persons or fixed surfaces, like people don't like to go through walls and so on, right? So that hinders people from going through their to the destination. Okay, so basically using this, we have an ordinary differential equation we are solving to generate passenger trajectories. So for each passenger, we can say at different times what was their position, right? And based on that, we can actually figure out who came close to someone else and so on. And we have some parameters for uncertain things, like for example, passenger velocity, the desired speed at which a passenger wants to go. Okay, what is the distance at which they want to stop? If someone is ahead, they stop at a particular distance, right? What threshold is that? Then people put, we have certain behavioral characteristics also. For example, people put luggage, store luggage in the bin, overhead bin. People may take different times to do that or to retrieve it and so on. So we have a few sources of uncertainty which are all parameterized. Okay. And based on that, we do these simulations, and then we look at different boarding strategies, and we can see over here, basically the idea over here is for different types of planes. You have still similar consequences, like if you do random boarding, you tend to have fewer contacts. If you have two sections, then you tend to have fewer contacts than having three sections, or a few other strategies like column-wise boarding and so on. Generally, in operations research, they have done a lot of analysis of efficient processes to move people into planes. Generally, moving people into planes, whatever is efficient for moving people into planes is actually efficient at spreading diseases also. Okay, so it'll be a little slower to actually move people into planes, but the difference is only about a couple of minutes. So if you tell people, do you mind getting Ebola, or do you mind getting in the plane 2 minutes later, we suspect people will choose getting into the plane 2 minutes later. Okay, so we can actually substantially reduce diseases using such strategies. I'm just giving you a kind of overview of the type of results we have generated. We had performed bottlenecks. Initially, the sequential computation itself sometimes took several hours, which was not very effective. We reduced the sequential computing time to the order of about 40 minutes or so. Actually, we reduced it around 20 minutes, but we did it in parallel. It took around 40 minutes due to inefficient parallel I/O. The Blue Waters team helped us reduce it to about 20 minutes maximum. This is a histogram. It's very unevenly distributed. Some simulations take a very short time. Some of them take a very long time. Okay. And so this is a contribution from the Blue Waters team. Then the main focus is on how to reduce the size of the parameter sweep. The conventional way of doing it is, let's say I have two parameters, then I choose, let's say, some 10 values for this parameter, 10 values for this parameter. I get 100 parameter choices that I can take. Okay, and one of the problems is that if I want to check whether it has converged, right? I do a lot of simulations. How do I know that I have covered the parameter space sufficiently that I have got all the scenarios? Then each of the convergence checks requires about 2 power d gap between convergence checks, where D is the dimensionality, that is the number of parameters. The other problem is that it also does not cover the space uniformly. For example, you can see in this direction, the space may be small. In this direction, there's a big gap. It doesn't cover the space very well. Okay. A random sequence, a pseudo-random sequence is better. The convergence check can be done within the factor of 2. Like I do 1,000 points, then I do 2,000 points, and then I'll check whether I have converged. Okay, so it is good in that. It still has a problem in converting the space because you can see there are some large gaps in some places, there are small gaps in other places. There's something called a low discrepancy sequence, which actually covers the space very uniformly compared to other sequences. It can also do a convergence check in a factor 2 gap. So we use a low discrepancy parameter sweep to actually cover the space. The lattice, even with 17 power 5 points, which is like about, pardon? Oh, okay. Even with about 17 power 5 points, it does not cover the space uniformly. It does not, the histogram does not converge, okay? And here with 17 power point, not only does it converge, even at this number of points, it's actually pretty close to what you have over here, okay? So maybe I'll cite a paper for you to look at if you want the details of this. So basically you can get a factor of 2 to 3 improvement, reduction in number of points you use just by using a low discrepancy parameter sweep, and it's a generalizable result. That is, it's not specific to this particular application. It just comes from the fact that it converges space. It samples the space more efficiently and also has more efficient convergence checks. Okay. Now, if you want to look at the load, the problem with the low discrepancy sequence though is that it has a big load imbalance. Okay, so if you look at the load imbalance, the conventional lattice sweep has a very low imbalance for reasonable processor sizes like 1024 or 1000, right, which are likely to use. With 1003, which is a weird number of cores to use, it has a slightly higher load imbalance for certain reasons given here. But the important point is that the low discrepancy sequence has load imbalance close to 1, which means that it's using double the time compared to what you should or ought to really be using. Okay? And the reason has to do with the fact that it does not cover the space in a random manner. It has some systematic pattern, and a systematic pattern depends on certain prime numbers that are used in the low discrepancy sequence. Okay, 1024 has one of those primes, and the prime obviously is 2 because that's the only prime that divides 1024. This also has a couple of primes 2 and 5 which are used in the low discrepancy sequence. We chose 1003 because 1003 is actually has no common prime factors with this, with the low discrepancy sequence, with the primes used in the low discrepancy sequence, and then the load imbalance actually goes away. So now you are using fewer processors, which means you are not using all the cores. You choose a certain number of nodes. Each node has 32 cores, but you lose only a small amount of computing power over here, but you save by a factor of 2 in the load balance. Okay, so that is if you do the whole simulation. There is also, but you normally don't know how many points you're going to generate. Rather, you do convergence checks periodically. So in that case, it becomes a little bit more complex. I will maybe not talk too much in detail, but the basic idea is that there are, if you can use a cyclic distribution or block distribution between each of those have different characteristics. In general, if you use a small number of points, the load is not very well balanced because the load in the sequence, each point is actually, each core is having something from a totally different point in the parameter space. Okay, whereas if you use lots of points, then all the cores are sampling reasonably from the whole parameter space, so they're all performing similar amounts of work. But using dynamic load balancing, you can actually reduce much of the performance overhead. Now to model infection spread, I think I'm kind of running a little short on time. So what I will do is I'll just show you the type of figures we generate. Okay, so we kind of we have a histogram for the probability of infection. Again, the probability should not be taken as an exact prediction, but rather you are comparing two different methods. Okay, because we say if people come a certain distance to each other, that the probability of transmission, that probability of transmission is not very clear. Okay, But relatively, you can compare two different methods to see one method is better than the other. And often we are interested in the extreme. We don't care about what is happening over here. We're saying, is there a likelihood of too many large amount of disease spread? Okay. So there are again, this is just a little bit more colorful, but more importantly, it includes the airport gates, and the previous one was for Ebola. Here we look at both SARS and Ebola. The important point is that there are many there's a big impact on the policies and how many days into infection are people there and all that in terms of the impact on disease spread. In the conclusions, I'll give you some actual conclusions we came to. The important thing here, the parameter sweep with the LDS in terms of computational optimization is much more efficient than a lattice. You can give orders of magnitude improvement. The load imbalance depends on number-theoretic properties. You can actually, if you know what primes are used, you can actually do something decent with load imbalance. Some of the results we came to are random boarding leads to lower risk of infection spread. The boarding has higher impact than deplaning infection spread, and smaller planes are better than large ones. Okay. And using a bunch of policies, we could have actually reduced infection spread by 87% without travel restrictions. There were travel restrictions, so disease didn't really spread much. But you can reduce the likelihood much without reducing air traffic. Okay, and in terms of future work, we are looking at using data into our simulation model so that our parameter space coverage is a little bit more efficient. Instead of looking at all possibilities that could happen, we actually say this is what is really happening. Then different cultures and all that have different population movement patterns. So we can use domain adaptation to do it a little bit more efficiently. And we are also looking at consequences of air travel. That is, someone comes into the country with a disease and spreads it into like Florida imported Zika into Florida, right? It wasn't endemic. So we use social media data to try to figure out how people are moving once they come into Florida. And the basic rule, moral here is that we are able to generate the risk map very efficiently. In fact, we are able to do it even to about a 1 square mile, order of 1 square mile radius within Miami. So we are able to come up with very fine-grained results. Okay, so we have more details on our project website.